I was asked to talk about the evolution of Earth, Venus, and Mars, but talking about those very different planets in 40 minutes or so is a bit challenging. So my plan is to focus on Earth, obviously the best understood planet, and see how we can apply our understanding of its evolution to other planets. Why we like to discuss Venus and Mars along with Earth is, of course, they are two most Earth-like planets in the solar system in terms of size and chemical composition, and yet they are still very different. So it's convenient to study and compare them to better understand the habitability of those planets. Those Earth-like rocky planets or terrestrial planets share an internal structure like this. We have a metallic core at the center, surrounded by a rocky mantle, and covered up by yet another rocky layer called the crust. And finally, the atmosphere, which could potentially include the oceans. Among these, the mantle is probably the most important component because it creates a crust by partial melting and the atmosphere by degassing. And it controls the cooling of the core as well. And if the mantle can cool the core efficiently enough, it can drive a planetary dynamo, creating a magnetosphere, which in turn modulates how the solar wind interacts with the atmosphere. So if you want to understand how a terrestrial planet evolves, you got to understand how its mantle works. Oh, sorry. Earth, Venus, Mars have very different surface conditions, which are dictated by the atmosphere. Earth's atmosphere is very unique, made of mostly nitrogen and oxygen with a bit of argon and carbon dioxide. But if you get rid of this oxygen, which originates from life, and release all carbon sequestered in sedimentary rocks, we get this kind of hypothetical atmosphere, which is very similar to that of Venus, and Earth will become a planet too hot for life to exist. So important question is why Earth isn't like Venus, why carbon is sequestered in rocks on Earth. And I think that it's because Earth has plate tectonics, which enables the so-called long-term carbon cycle. I think this will be covered in greater details by later talks. So I just briefly note that the amount of carbon dioxide in the atmosphere is a result of dynamic balance between volcanic input, chemical weathering, sedimentation, and subduction. And subduction is possible only with plate tectonics. And if you have life that can do photosynthesis, it also activates the organic subcycle in which subduction contributes to the net production of oxygen as well. Venus and Mars don't have plate tectonics. They have instead stagnant lead convection. In a stagnant lead convection, a planet is covered by a single rigid lid, and convection can take place only beneath the lid. Mantle still can melt and degas, so it can create the crust and the atmosphere, but it's a one-way mass transport from the interior to the surface. In plate tectonics, on the other hand, surface layer can be recycled back to the interior, so we can have geochemical cycles. Okay, so this one-way versus two-way mass transport is probably the most important difference between stagnant lead convection and plate tectonics. So we have to wonder then why we have these two modes of mantle convection. Okay, how does a planet decide which way to go? It turns out it's very easy to explain why Venus and Mars have stagnant lead convection, because that's the most natural way for silicate mantle to convect. Viscosity of silicate rocks is extremely sensitive to temperature, following the so-called the Arrhenius form, and it changes over many orders of magnitude for range of temperature expected within a planet. Here I'm showing two different convection movies with the same internal viscosity. The top one is ice viscous case, meaning that the surface viscosity is same as the internal viscosity. Temperature here reflects color here is reflects temperature. Red is hot and blue is cold. And this green dot, maybe you cannot see here, but green dot is a passive tracer just to visualize how things are moving around. This is the so-called Rayleigh-Benner convection, the simplest kind of thermal convection you see in a textbook on fluid mechanics. But if viscosity is as temperature dependent as silicate rocks, because of this temperature dependent viscosity, the most of boundary layer is too stiff to deform, and only the lowermost fraction of the boundary layer can participate in convection. And this is what we call as stagnant lead convection. But Earth doesn't have stagnant lead convection. It has plate tectonics. And it's very puzzling from the perspective of rock mechanics. Okay? Because plate tectonics is happening on this planet now, and because the discovery of plate tectonics revolutionized many branches of Earth sciences, many people tend to take it for granted, but it's important to understand it's still difficult to explain plate tectonics from first principles. So we still have these major questions. Why does it happen on Earth? How has it evolved? And when did it start? Okay. We have a really good understanding of how plate tectonics has behaved in the last 180 million years, for which we have a direct record of C-frost plating, but that's a very small fraction of 4.5 billion years of Earth history. In this talk, I try to give my the most up-to-date account on those issues. I'd like to start with a quick tutorial on mantle convection. Just to have everyone on the same page, I start with a simple Rayleigh-Benner convection. Convection is a combination of two modes of heat transfer, conduction and advection. And if you heat up a layer of some fluid from below, heat is first conducted at the bottom boundary, and then heat up a fluid, then goes up by its own buoyancy. This is advection. Then loses heat at the top boundary, again by conduction, and then cool down fluid sinks by negative buoyancy. This is also advection. Thermal convection is this cycle of conduction and advection. Boundary layers grow by conduction, and their thickness follows this diffusion scaling. Here, kappa is thermal diffusivity, and T is time. So when things are moving faster, you have thinner boundary layers because they don't have much time to grow. Mantle convection is different from the Rayleigh-Benner convection in a few important ways. First of all, they are primarily driven by cooling from the above. Rayleigh-Benner convection is quite symmetrical. Heat getting out of the above is same as the heat getting into the bottom. But in mantle convection, surface heat flux is much higher than the bottom heat flux because of internal heating. And because of that, top boundary layer, which we call lithosphere or plate, plays a much more important role than the bottom boundary layer. And because of temperature dependent viscosity, this top boundary layer or lithosphere is very, very stiff. And mantle also melts upon upwelling, and this partial melting of the mantle creates oceanic crust, and also a leftover mantle called the depleted mantle lithosphere. And so the evolution of top boundary layer or lithosphere reflects this chemical differentiation as well as cooling from the above. And on top of that, mantle convection can exhibit open system behavior, for example, by exchanging water with oceans by degassing and regassing. Present-day mantle is known to contain a bit of water, and this partial melting acts to remove such water from the mantle. The viscosity of the mantle not only depends on temperature, but also depends on the amount of water in it. So if this degassing and regassing are not balanced, you're gonna change the amount of water over time, which in turn changes the viscosity of the mantle. Okay, so we are now ready to discuss two conditions for plate tectonics. First condition comes from chemical buoyancy. As I mentioned in the previous slide, the partial melting of the mantle creates oceanic crust and depleted mantle lithosphere, both of which are actually more buoyant than the underlying mantle. That is, they act like a rubber duck. And as you know, a rubber duck doesn't want to sink. The only way to make it sink is to add some anchor And in this context, plate has to grow thick enough so that its negative thermal buoyancy can cancel its positive chemical buoyancy. The second condition is, of course, plate has to be weak enough to bend and subduct. Okay, and because of these two conditions, even though we know plate tectonics is happening on Earth today, it's not that easy to figure out if plate tectonics operated in the past. First, we have a chemical buoyancy problem. This diagram shows how mantle melts, and this is temperature, and this is depth. When mantle upwells, it hits the solidus and starts to melt, and this melting creates oceanic crust and depleted mantle lithosphere. When the mantle was hotter in the past like this, it hits the solidus at a deeper level, melts more extensively, creating thicker oceanic crust and thicker depleted mantle lithosphere. With the rubber duck analogy, we must have had a bigger rubber duck in the past. So if you want to have plate tectonics, the plate has to become very thick. And for this to happen, the tempo of plate tectonics has to be slower in the past, because you cannot have thick boundary layers when things are moving fast. But at the same time, thicker plates are more difficult to bend and subduct. The situation gets worse if you think about another criterion, that is, plates have to be weak enough to bend and subduct. Based on theoretical studies, we know that the viscosity of lithosphere cannot be too high. The contrast between lithospheric viscosity and internal viscosity has to be lower than 1,000 to 10,000 under Earth conditions if you want to have plate tectonics. Okay? And because we have plate tectonics today, we know that the contrast, present-day contrast should be lower than this threshold. Now, if you think about the situation in the past, mantle was hotter in the past, so its viscosity was lower. Okay, so we have lower internal viscosity, but lithospheric viscosity should be more or less the same because it just depends on surface conditions. So what this means is that viscosity contrast is expected to be greater in the past. That is, even if this condition is satisfied at the present day, it's not that clear if this condition is satisfied in the past because we have a greater viscosity contrast in the past. This viscosity problem is at the core of the physics of plate tectonics. So I'd like to spend a few slides to go over relevant basics. First, how do you quantify the strength of lithosphere? We have two choices, viscosity and yield stress. I hope you know that viscosity is a proportionality factor for the relationship between stress and strain rate, and how much of stress do you need to achieve a certain rate of deformation varies among different materials, and this material dependency is captured by viscosity. So for example, viscosity of water is 10 to the minus 3 Pascal second, that of peanut butter is 100 Pascal second, and that of mantle rocks is much, much higher, on the order of 10 to the 18th Pascal second or greater. When it comes to describe the strength of lithosphere, we can use this viscosity or yield stress, which is the amount of stress you need to achieve a strain rate of 10 to the minus 15th per second. This is a so-called geological strain rate because it's representative of typical geological deformation. So if you know a value for viscosity, you just multiply with 10 to the minus 15th and you get the corresponding yield stress. This yield stress is actually more convenient because it's not limited to viscous deformation processes. It's a more general way to quantify material strength. So let's see how viscosity or yield stress changes across the typical lithosphere. This axis is depth, and this is corresponding temperature. We are looking at the top 100 kilometers of terrestrial planets. This is viscosity, and this is corresponding yield strength. Yield strength in the megapascal. So shown here in red is one kind of temperature-dependent viscosity based on diffusion creep. And oh, by the way, so this particular example assumes the internal viscosity of 10 to the 19th Pascal second. So this is the internal viscosity. And if you remember, to have plate tectonics, viscosity contrast between the lithosphere and the interior should be lower than 10,000, or in terms of yield strength, it should be lower than 100 megapascal. So if you just have this diffusion creep around, we clearly cannot have plate tectonics. We have another kind of creep mechanism called dislocation creep, which helps a bit, but not much. Both diffusion creep and dislocation creep are so-called high temperature creep, which are effective, of course, at high temperatures. And the lower temperatures, we have low temperature plasticity, which goes like this. And at lower pressures, things can deform by brittle failure. And finally, we have also semi-brittle deformation regime, which smooths out the transition from brittle to plastic deformation. Lithosphere deforms with the lowest possible yield stress, as shown by this yield envelope. But you can see, with all of these deformation mechanisms known for silicate rocks, we still cannot satisfy the viscosity contrast criterion for plate tectonics. So we need something more, and there are two weakening mechanisms that are consistent with rock mechanics. One is grain size reduction. This diffusion creep, this red line, is actually dependent of grain size. And here I'm using a typical grain size of 5 millimeter. But if you use a much smaller grain size, like 100 micron, forward. 100 micron, you can reduce yield stress like this. But this grain size reduction doesn't do much for the hardest part of the lithosphere. On the other hand, a mechanism called thermal cracking can directly affect the brittle deformation, and it can reduce the yield stress like this, and we can finally satisfy the viscosity contrast criterion, and we can have plate tectonics. The only caveat is that for this thermal cracking mechanism to be fully effective, we need to have surface water. So viscosity contrast is just below the threshold at present. So if you want to have plate tectonics in the past, you don't want to increase the contrast because you might overstep the threshold otherwise. The only way to avoid such an increase in viscosity contrast is to have a drier mantle in the past. The warm and wet mantle at present and the hot and dry mantle in the past can have similar viscosity. And this scenario is possible if regassing is more efficient than degassing. That is, the mantle is gradually hydrated by subduction, and we had deeper oceans in the past. Several different lines of evidence suggest that this is actually what's happening, and I'm going to talk about this a bit more later. So where to have water is important if you want to have plate tectonics. If you don't have any water, either on surface or interior, you have stagnant convection because lithosphere is just too strong to deform. If you have surface water and a dry mantle, that's an ideal combination, and you likely have plate tectonics. If you have no surface water, but a wet mantle, you start with stagnant convection, but stagnant convection can degas to produce surface water, which may promote the onset of convection afterwards. And a similar thing can happen with a combination of surface water and a wet mantle. But to be honest, it's not a clear cut, and there are lots of question marks because these things depend on how hot the mantle was at the beginning and how much water we start with. So this is the kind of caveat. This is Earth-sized planet in the habitable zone with a modest amount of initial water. Okay, so that concludes my tutorial on mantle convection, and now we can finally come back to these questions. First, why does plate tectonics happen on Earth? As I mentioned earlier, the most practical mechanism is weakening by thermal cracking, but this thermal cracking mechanism is actually not a very simple process, and we still don't have a complete understanding of how it's going to work. And we have only a few pieces of indirect evidence for its operation. But as of now, this is only mechanism that is consistent with rock mechanics and can weaken lithosphere substantially. So stay tuned for future progress. We actually have a better understanding of how plate tectonics has evolved. I hope you've heard the supercontinent Pangaea, which formed about 200 million years ago. And Pangaea was the most recent supercontinent. And we had 4 more supercontinents: Gondwanaland, Rodinia, Nuna, and Kenoaland. And now, if you want to make a supercontinent from the by assembling scattered continents, you have to close ocean basins between continents, for which you need to have subduction, that is plate tectonics. The oldest supercontinent, Kenoaland, was formed about 2.7 billion years ago. So we can trace the operation of plate tectonics at least back to 3 billion years ago. The chemical buoyancy criterion requires thicker plate and slower plate tectonics in the past when mantle was hotter, creating thicker oceanic lithosphere, thicker oceanic crust and thicker depleted mantle lithosphere. And this notion of slower plate tectonics in the past turns out to be consistent with the range of geochemical and geological data as listed here. Slower convection when things are hotter may sound counterintuitive from the viewpoint of fluid mechanics of simple fluids, but mantle is not a simple fluid. And the viscosity contrast criterion requires non-zero water flux from the ocean to the mantle, which is also consistent with the understanding of deep water cycle based on present-day fluxes, numerical modeling, and the constancy of continental freeboard. Just to have a feel for these, for the magnitude of those numbers, with influx of 3 times 10 to the 14th gram per year of water, the present-day oceans can be drained within 4.5 billion years. So those numbers are quite substantial and sufficient to modify the viscosity of mantle to help the operation of plate tectonics. And finally, when did it start? Did we have plate tectonics beyond 3 billion years ago? Figuring out, well, this doesn't look clearly. Okay, figuring out the onset of plate tectonics is really hard because plate tectonics keeps erasing evidence of its operation by subduction. As you can see here, so we need to look for traces left on continent. As you can see here, this is a map of crustal age. Oceanic crust is no older than 200 million years, but continental crust can be billions of years old. So we can hope that the way continents have evolved may reflect the history of plate tectonics. Just in case you don't know, Earth have 2 kinds of crust, oceanic crust and continental crust, and they are both products of mantle melting, but they have different chemical compositions, and it's more involved to make continental crust than oceanic crust. And usually believe that making a continental crust involves the subduction water by plate tectonics. Now, I'm very glad to give this talk this year, 2019, because studies on continental growth has been quite confused state for the last 3 decades, and especially from 2010 to 2017. And I use the word classical in a different way from Sean. This is a great, like 80s was a truly great time in many aspects. And anyhow, so because of that, it was almost impossible to give a sensible talk on the evolution of continental crust until recently. Although I should warn you that many people still live in these dark ages, but you guys don't have to worry about that. One of the problems is that there are just so many different looking models proposed for continental growth, as summarized this figure. Mass of continental growth is usually normalized by the present day value. So all models converge to 1 at present. But besides that, things are all over the place, as you can see. The most problem is, however, that many of those models are actually not about continental growth, but people didn't realize that for a long time. It turns out you can classify these models into 4 groups: mantle-based, crust-based, others, and artifacts. And the mantle-based models are they are like a true continental growth model. They're about net crustal growth. And they tell us how much of continental growth we might have had in the past. But this crust-based model is just a distribution of formation ages for the crust we have today. The continental crust that has been preserved to the present day. So these are different. And I'm gonna go back to this important difference later. These others are mostly speculations. And 4th category is just a mere artifact. Interestingly, those artifacts have been the most popular models in the last several years. And this has been the source of great confusion in the literature. But we don't have to worry about those 2 categories, and we should focus on the top 2. Shown here are the latest mantle-based model and the latest crust-based model. And again, a mantle-based model tells us net crustal growth, how much of continental crust we had in the past. So this model in red says that the amount of continental crust increased very rapidly in the early years and reached the present day level at 4 billion years ago. So, okay. This crust-based model in blue is a cumulative distribution of formation ages of the present day continental crust. So from this curve, we can tell, for example, about 20% of the crust we have now was formed before 3 billion years ago. Okay. This curve doesn't mean 3 billion years ago, the amount of continental crust at that time is only 20% of the present day level. Okay. We could have more, but it just it just didn't survive to the present day. Okay. So even though these 2 models look very different, it doesn't necessarily mean they are inconsistent to each other. The difference between these 2 curves simply reflects the effect of simply reflects how much of continental crust has been lost to the mantle by crustal recycling, which is possible with plate tectonics. Now, the most exciting thing about these 2 models is that we can actually show that these 2 models are fully consistent to each other, because this net crustal growth model, shown in red, is built by so-called geochemical box modeling, which comes with its own estimate on crustal recycling, shown here. Net crustal growth and present-day distribution of formation ages are 2 aspects of the same crustal evolution, and they are therefore connected. And their relationship can be written down using integrals and the differential equation. For example, here, t is time and tau is formation age. And if you integrate formation age distribution at time t, it should equal to that crustal mass at the time t. And this formation age distribution is modified by new crust generation and crustal recycling. So if you have a model of net crustal growth with crustal recycling, you can integrate this differential equation to calculate corresponding formation age distribution at the present day. So again, coming back to these 2 models, this net crustal growth model is built by geochemical box modeling, which comes with its own estimate for crustal recycling. So by combining these, we can calculate corresponding present-day distribution of formation ages, which look like that. So it matches fairly well with the crust-based estimate. And this agreement is rather remarkable because those 2, the zigzag line and this blue shade, are built on 2 entirely different geochemical data and by 2 entirely different methods. This kind of agreement rarely happens in earth sciences. So continental crust may have grown very rapidly in the early Earth, and at the same time, crustal recycling was intense. Constant crustal mass with non-zero crustal recycling means that we need to keep generating new crust at the same rate of crustal recycling. So we have a persistent crustal recycling and crustal generation throughout Earth's history. The most straightforward interpretation of this is that plate tectonics has started right after the beginning of, and right after the solidification of pure magma ocean. But if you look at this figure, the rate of crustal generation in the early Earth is really intense. And this raises a question as to what kind of mantle dynamics was responsible for this rapid crustal growth. As I mentioned earlier, tempo of plate tectonics must have been slower than present, at least back to 3 billion years ago. But plate tectonics in the early Earth may have behaved very differently. For this reason, my group has been working on the physics and chemistry of magma ocean, and our first result got recently published in JGO. And I don't have much time to talk about these results here, but upshot is that the kind of mantle you likely get after the solidification magma ocean is this kind of chemically heterogeneous mantle with small-scale crustal blobs embedded in a highly depleted mantle matrix. This chemically heterogeneous mantle can give us a radically new picture of mantle dynamics. If the mantle is chemically more homogeneous, as usually assumed, then this upwelling of hot mantle produces thick basaltic crust, as shown to the left. But if mantle is chemically heterogeneous, or more specifically, small-scale crustal blobs are embedded in highly depleted mantle rocks, then the upwelling of such mantle expose this mantle expose directly this mantle matrix, because those mantle rocks are already too depleted to melt further. Okay, and these small-scale crustal blobs are likely hydrated because they are leftover of fractional crystallization. So the partial melting of those hydrated crustal blobs could produce felsic crust, which is important if you want to make a continental crust. One thing I like to emphasize is that these two different kinds of mantle have same bulk composition, but the difference in the scales of lithologic heterogeneities can give rise to very different types of magnetism and mantle dynamics. So with the chemically heterogeneous mantle, we could have had abundant exposure of mantle rocks at seafloor, and this period, mantle rocks can intensely interact with seawater, which could generate lots of hydrogen, and also it could sequester lots of carbon dioxide. And the melting of those hydrous crustal blobs could generate felsic early continental crust. And more importantly in this context, the lack of uniformly thick buoyant oceanic crust facilitates rapid subduction, that is rapid plate tectonics, and which could cool the core very efficiently, which may allow the onset of early geodynamo. The possibility of rapid plate tectonics in the early Earth is attractive in many ways. I think Kevin is going to talk about this later, but in early atmospheric evolution, people usually assume rapid sequestration of carbon dioxide, like this, shown by this dashed green line. At the beginning, Earth may have had a very thick Venus-like carbon dioxide, 100 bars of carbon dioxide, but it has to be quickly sequestered down to 0.1 bars of carbon dioxide in time scale, 100 million years. I used to wonder how this could be geodynamically possible, because I thought tempo of plate tectonics should be slower in the past, but now I think it's not that difficult to explain this if the solidification of magma ocean results in a highly chemically heterogeneous mantle. So to summarize, what I think about the likely evolution of plate tectonics on Earth, plate tectonics probably started right after the solidification of magma ocean, but the tempo of plate tectonics was probably very fast because of chemically heterogeneous mantle. But these chemical heterogeneities were gradually erased by convecting mixing, and it switched to the slow pretectonics mode with homogeneous mantle. And with the start of pretectonics, subduction water starts, and the initially dry mantle gradually gets hydrated to become a present wet mantle. And this transition from dry to wet mantle is important to maintain long-term operation of pretectonics. And the subduction water is also responsible for the eventual emergence of continental crust above sea level, which affects surface environment a lot. And I hope later talks touch upon this issue. So coming back to this slide, these 4 scenarios are for Earth-sized planets in a habitable zone with a modest amount of initial water. So if you deviate from these qualifiers, you have a different story. So we can finally discuss why Venus and Mars are so different from Earth. We have some geochemical evidence that suggests Venus had surface water in the past, but Venus is simply just too close to the sun. The solar influx is greater than its radiative limit, so surface water got quickly lost to space by a runaway greenhouse. And if you lose surface water, then you only have stagnant convection as an option. Mars also had some water, but lost most of it because its gravity is too weak to hold it. And so again, it ends up with stagnant convection. We don't know much about how much of initial water we had in the mantle for Venus and Mars, but it doesn't really matter because if you cannot maintain surface water for a long time, it's very difficult to have pretectonics. Now, even for an Earth-sized planet in the habitable zone, if you have too much surface water, like in the water world situation, you wouldn't expect the operation of pretectonics because the lower half of the surface water would be ice, which doesn't help the operation of pretectonics, even with thermal cracking. Okay, for thermal cracking to be active, you have to have a fluid phase. So to conclude, pretectonics has probably been operating on Earth since its beginning, soon after the solidification of magma motion. But it doesn't mean that it's easy to have pretectonics. Okay, its operation hinges on a delicate balance of water effects, the different kinds of water effects. Okay, so it's not to keep pretectonics. Even though if you happen to have a pretectonic sometime during planetary evolution, it's not easy to keep it for a long time. The right heliocentric distance, right amount of initial water, preferably on surface, and the right size are all important if you want to have Earth-like planets. And the 2 key issues for the general theory of the evolution of terrestrial planets are 1, conditions for pretectonics, and 2, the effects of pretectonics on surface environment. From exoplanetary perspective, the second issue probably is very important, but to study this, we have to model for which the first issue becomes critical. And I hope that future exoplanetary observations may provide some clues to resolve those issues. Thank you.
Thanks. Yeah. So in your red curves on your most recent Korenaga paper,
yeah,
how much dry land or at least subaerial land is represented in those curves?
Oh, this is okay. So that's a good question. So they are just how much of continental crust we have on the surface. Okay, it doesn't mean we have all those continental crust above seawater. Okay, so it's based on how much the extent of dry land depends on both continental mass and bathymetry and how much water you have at the surface, and it's highly model dependent. But whatever you do, you tend to end up with you have like a mostly water world before 3 billion years ago. So you have, so it's much easier to have exposure of dry landmass after 3 billion years. But before that, it's kind of hard. Yep.
Can I get a clarification on that? Because I also have the same question. So there was freeborn early. I mean, you had cratons, small cratons early. Okay. Or how many millions or hundreds of millions of years does the production take before you make planet?
Okay, no, I mean, okay, continental crust, like, like granitic rocks and dry land are two very different stuff. Okay, even if you have thick continental crust, it doesn't have to be above sea level if you have too much water or seafloor is too shallow. Okay, so right. Oh, okay. So having, okay, oceanic crust and continental crust, they have different densities, but this different density difference alone doesn't make continental crust above sea level. It's very, I think it's kind of common misconception, but the relationship between this mass of continental crust and how much of dry land we have above sea level are two very different problems. Okay, so you need to know. Okay, so this is, you can tell about this purely based on geochemistry, but to tell how much of dry land you had in the past, you have to combine much more information. Okay, to build an integrated model for continental freeboard and sea level. So based on that, I can tell you that it's easy to have dry land after after 3 billion years, but it's more difficult to have dry land before 3 billion years ago. Okay, yeah. Yes.
I don't think the astronomers in the room are going to know what craton, mafic, are. Clarify some of these terms. Why do you use them?
Okay. Yeah. So maybe I should go back to this one. So, well, okay, this slide doesn't. So we have continents and ocean basins, right? And oceanic crust is, present day, is not that thick. Oceanic crust is only 6 to 7 kilometers thick. But typical, like average thickness for continental crust is like 40 kilometers. It's much, much thicker. And this is the one reason why those continental crusts are mostly above sea level. Okay. And as I mentioned briefly, both types of crust are products of mantle melting. So they all originate in the same mantle, but the process involved for the formation of oceanic crust and continental crust are very different. So it's kind of funny because in Venus and Mars, we don't have any oceans, but the kind of crust they have is oceanic crust. Okay, to have crust, if you melt mantle by single stage melting, then you have kind of crust what we call oceanic crust. But to have continental crust, you have to process further this oceanic crust to get a more evolved chemical composition, which is important to have a different densities and different densities and so on. So so that's so oceanic crust in terms of kind of geological jargon have a chemical composition called mafic, and a continental crust is a felsic chemical composition. Okay. And cratons are, yet another geological jargon, refers to a very old and stable part of continental crust. And we have quite a few, because this corresponds to this very red region here. So we have maybe 10 or 20 different cratons scattered around the globe. And they are very important repository for ancient Earth history.